The race to scrub the sky started over 400 years ago, in the days of King James I. Unbeknownst to the players involved at the time, the technology they came up with could very well play a key role in the race to combat the climate crisis in the years to come. Welcome to Scrubbing the Sky, a podcast series about the race to scrub carbon dioxide from the atmosphere at a planetary scale. I'm Ed Whittingham, co-host of the Energy vs. Climate podcast, and I'll be your host for this series inspired by the book, Scrubbing the Sky, Inside the Race to Cool the Planet by author Paul McKendrick. Both the book and the podcast tell the stories of the scientists, philanthropists, investors, and advocates involved in that race. This first season focuses on direct air capture, also known as DAC, one of the leading technology pathways to take carbon dioxide out of the atmosphere. For those companies that can successfully bring this technology to market, well, it could be a massive windfall. And for the planet, it could help avert disaster. The story starts 400 years ago, on a fine spring day in the 1600s, back in the time of King James I of England. The king asked a Dutch inventor named Cornelius Drebbel to create a laboratory in the royal palace and design apparatuses that replicated phenomena found in the natural world. Here's author Paul McKendrick to help unpack what exactly happened back in 1620.
Cornelius Drebbel was this super fascinating Dutchman who invented all sorts of things. His most noteworthy invention was the submarine. It was the first submarine ever built, and they were built out of wood that was covered with greased leather to seal them, and they were propelled by oars sticking out the sides through leather seals. The biggest challenge, though, was designing a way that the people inside the submarine could continue to breathe for an extended period of time as they were breathing in oxygen and exhaling carbon dioxide. This was 100 years before carbon dioxide was even officially discovered. Yet Drebbel devised this way, what now is called a rebreather, which has a scrubber that effectively takes carbon dioxide out of the air. And there's no definitive evidence for how Drebbel's scrubber worked, but it's believed that he heated potassium nitrate, which is also known as saltpeter, in a metal container, and that produced oxygen and potassium oxide, which is known as hydroxide. And it was the potassium oxide, that absorbed carbon dioxide from the air. So according to accounts from the time, it seems that he was safely able to transport 12 passengers down the Thames from Westminster to Greenwich, which was roughly a 3-hour journey, with the king himself on board.
Wait a minute, you're saying that in 1620, he was able to design a submarine that traveled 3 hours from Westminster to Greenwich, and people didn't die.
That's correct. And so, this was, 3 centuries before submarines came into widespread use in World War I. And now, 4 centuries after Drebbel first used the scrubber on the Thames, it might now be a precursor to helping scrub the sky of excess carbon dioxide.
Now, even though Cornelius Drebbel was ultimately unsuccessful in finding someone to bankroll this invention, he managed to prove something. Through a straightforward chemical reaction, enclosed air, like the air in his submersible invention, could indeed be scrubbed of carbon dioxide. So let's fast forward to today's climate change crisis. We're way past the point where we can fix the climate crisis by just stopping emissions. We still have to stop them, but we also have to figure out a way to start actively removing carbon dioxide from the air as well. Think about the problem like a bathtub slowly filling up with water. The bathtub is the atmosphere, and the water is carbon dioxide. Now, a certain amount of water in the bath is fine, but if it spills over the edge of the tub, well, we wreck the house. To avoid that, the first thing you do is turn down the flow of water into the tub. That's reducing emissions that we put into the atmosphere. But a slow trickle will still cause the tub to overflow, so we'll also need to drain some of the water out of the tub. And that's carbon removal. Or in other words, moving carbon from air to underground, or to rocks, or even to oceans. That perfect balance between water slowly trickling into the tub and water draining out of the tub is the net zero part that we talk about in, say, net zero commitments. David Keith is a climate scientist who, since 1990, has spent almost all of his professional time on the climate challenge. He is the founding director of the Climate Systems Engineering Initiative at the University of Chicago, as well as the founder of Carbon Engineering, one of the 2 companies in the world today building direct air capture plants at commercial scale. David is also a friend and a fellow co-host of our Energy vs. Climate podcast. We've known each other for over 20 years, and we work together on a number of climate-related initiatives. So I biked over to his Canmore house to talk about carbon removal.
Hey, David.
Hey there.
Hey, cool wall.
Yeah, it's our climbing wall. This is the big elaborate. It's like all day we keep that shearing.
First off, the very basic thing, what is carbon removal?
Carbon removal is trying to undo what humans have done by burrowing into the earth and getting all those fossil fuels out and putting them into the atmosphere, or then equilibrate with the land biosphere and the oceans. And so to me, carbon removal is trying to reverse that process by taking carbon out of the active biosphere, out of the atmosphere, but also out of the active carbon out of the oceans and putting it back into long-term storage.
So why does it matter? And I think you wrote a New York Times article in which you said there are only 2 ways to cool the planet in this century, and one is through carbon removal and the other is through geoengineering. Why did you say that, and why this century? Like, why isn't, we're building solar at the rate of knots. Why will that not cool the planet in this century?
So maybe the most important single fact about climate change is that at least over roughly this century, a warming is proportional to cumulative emissions. So that means that the emissions each year really aren't the deal. It's the emissions over all the industrial era. Mm-hmm. And that also means when you bring emissions to zero, you've stopped adding to the accumulation, but you haven't reduced it. So when you bring emissions to zero, you'll stop warming the planet, but you won't cool it off. And cooling off the planet by just waiting takes of order 10,000 years.
That's good. We talk about net zero by 2050 because governments, policymakers, activists seem to have this myopic view of net zero by 2050. But I think what you're saying is by 2050, if we achieve net zero, we'll just be baking in the degree of warming that by 2050, and that degree of warming might be unacceptable.
Personally, I think the chance of getting to net zero by 2050 is very low. I also would question whether that is, in any case, an ethical target anymore. But I think whatever the target is, what is certainly true is when the world gets to net zero, we have the climate change we have. And if you just stayed at net zero after that, you'd be at whatever warm state you were then for essentially forever, for 10,000 years. And in general, things would not get any better. And some things like glacier melting would keep getting worse.
We've got this level of warming above pre-industrial that we're at now. We're continuing to emit. The warming problem will get worse.
Any given time, the warming is due to historical emissions. Additional warming comes from additional emissions we make. So what emissions cuts do is they stop the additional emissions. They stop us making the problem worse. Mm-hmm. But emissions cuts cannot do anything about the accumulated historical emissions, the accumulated carbon burden. The only ways to deal with the accumulated carbon burden and the temperature it necessarily creates are either to take the carbon out, which is the only really long-run safe way to do it, or to do solar geoengineering, which reduces some of the climate changes for a given amount of carbon in the air.
Mm-hmm. When people talk about carbon removal, they talk about long-duration carbon removal and short-duration carbon removal. And moreover, on long-duration carbon removal, people talk about on a geologic timescale. Can you explain the difference between the two?
I think the best way to divide up carbon removal technologies is according to the form that the carbon is stored in after you've removed it. So there's really only 3 options. You can either take the carbon dioxide out of the atmosphere and then you've got a gas. That's one option. And that could be done by direct air capture or by biomass wood capture. Those both get you a carbon dioxide gas that was in the atmosphere. Or you could do things that make a dissolved salt.
It may sound a bit odd, but converting carbon into a salt is entirely possible. For instance, if you leave a glass of water out on your counter long enough, it will slowly become acidic through the natural process of being exposed to air. The CO2 in the air reacts with the water and produces carbonic acid in the water. Now, if you drop an antacid tablet, which contains magnesium oxide in that glass of water, it'll neutralize the acid and create a base. Then the water will suck more CO2 out of the air until all the magnesium oxide from the tablet plus the carbonic acid have been converted into a dissolved salt, which can then go into the ocean, land, or be converted into the organic carbon found in trees and soil.
So the 3 options are organic carbon, dissolved salts, or carbon dioxide gas. And in general, dissolved salts are inherently stable on geologic time. If you take CO2 gas and you do geological storage, it's there permanently. There are issues about leakage, but they're really small. The IPCC report that I was part of estimated that leak rates in 1,000 years would be less than 1%. So we can call that effectively perfect. If you get carbon into organic material, there's the fundamental fact that things like to eat other things. Organic material wants to oxidize. It thermodynamically wants to react with oxygen to go back to CO2, and all sorts of living beings and microbes that rot things want to do that. And so in general, organic carbon storage will always be pretty short term. If you think of trees and surface soils, think years to many decades. But there are definitely organic storage methods that might be much longer. So people are taking trees and or other organic material and making high density bricks from them and burying those bricks. And that storage is probably thousands of years.
Got you. And then that gets to the differentiation. So we talk about short-term versus long-term.
The only real closed system is DAC.
Okay.
Where DAC is something that more or less you can regard as a box where you put money in, you put energy in, and CO2 comes out.
So what is direct air capture and how does it work? Simply put, direct air capture, or DAC as it's known by its acronym, is the direct removal of carbon dioxide from the atmosphere using chemical technologies and industrial equipment. In other words, it's not unlike what Cornelius Drebbel came up with in the 1600s. And though scientists have known about this technology for over 400 years, it's only recently that it has shot to the limelight as we race to cool the planet. In the world of DAC, Klaus Lackner is an important name. For some, he's considered the grandfather of direct air capture technology. Here's author Paul McKendrick.
Klaus Lackner is by all accounts a genius. When you're talking to him, it quickly becomes apparent that he operates on a much different level. Originally, he's from Germany. That's where he was born. When he was a teenager, he read a book called 1, 2, 3, Infinity. It was written by a physicist named George Gamow. And it provides an entertaining introduction to science. And it was impactful on Klaus. And so it led Klaus down the path of studying physics. And eventually he made his way to the U.S. And so he went on to spend some time at the U.S. government's Los Alamos National Laboratory, which was established in World War II to design atomic bombs. But as the Cold War was ending in the 1990s, the lab needed a new reason to be. And so focus shifted to other security threats like climate change. And thankfully, Klaus also shifted his focus to studying climate solutions.
And tell me, like, there's this idea that Klaus and his friend Christopher Wendt had that some of the world's biggest problems could be solved with large colonies of self-replicating machines. Do I have that right? And if I do, can you tell me more about it?
Yeah, that's right. While Klaus was still a scientist at Los Alamos in New Mexico, he was on the back deck of his house one evening in 1992 with a friend, and they were reminiscing about how people used to dwell upon big ideas more frequently when unintended consequences were less of a reality. And so a few beers in, the two came up with a big idea of their own. And that was, what if some of the world's biggest problems could be solved by having large colonies of self-replicating machines? And so these self-replicating machines, which they later dubbed auxins after the Greek word for grow, they would dig up tons of raw dirt, they would sift through it for minerals and metals, they would transport it, they would manufacture machine parts and solar panels and build more of themselves. And Klaus envisioned a self-maintained system that would function around the clock with minimal human oversight. And so as they looked out upon the Mesa landscape in front of them, where atomic bombs used to be tested, they envisioned that area could host enough solar panels to power all the US, and then other machine colonies could address other societal needs, like, for example, cleaning up the excess carbon dioxide that's building up in the atmosphere.
After Klaus tested the auxons, they found no obvious roadblocks. So as scientists do, they co-authored a paper. And for a while, that was the end of it. Klaus moved on to other things. But the auxon paper had sowed the seed of capturing carbon dioxide from the atmosphere in Klaus's mind. However, as Klaus told me when I interviewed him back in 2022, the greater challenge would be finding a place to safely store all that CO2 that would need to be removed from the atmosphere in a world that continued burning fossil fuels.
If you ask me, can I store a ton of CO2? Of course. 1 million ton, not a problem. 1 billion ton, take a deep breath, and it can do that too. If you look at how much CO2 we could put out this century, it's on the order of one Lake Michigan. If we're really good, it's half a Lake Michigan. If we're really bad, it's 2 Lake Michigans. And right now we are looking like we're getting better. But we are 40 gigatons a year right now. So this would be 4,000 gigatons in a century. And Lake Michigan is 5,000 gigatons of water. We know that we can pull kinetic energy out of the air. Why couldn't we pull CO2 out?
I'll spare you the nitty-gritty details, but after giving some thought to the economics of how windmills capture air to produce energy, Klaus figured there's no reason why we couldn't also capture air to produce carbon dioxide. Now, Klaus had the idea to build a machine that can pull carbon dioxide back out of the atmosphere. He knew that in theory, doing so shouldn't cost too much because windmills are financially profitable. So what happens next? Well, Klaus got a helping hand from an unexpected source, his 13-year-old daughter, Claire.
I was sitting and working at home on a weekend. My daughter walks into my office and she said, I need a science fair project. What would you suggest I might look into? And I said, how about collecting CO2 from the atmosphere? So she goes away and she comes back and she has a plan. She says, I'm going to get myself, I had explained calcium hydroxide, and she was the age where she learns all of that stuff. And she said, okay, if I get an aquarium pump and will bubble air through this solution, would it collect CO2? And I said, my guess is yeah. So we designed a little experiment and she ran it. And my contribution to this experiment was, because I'm a night owl, at midnight I would make sure there's still water in it, because otherwise it'd be dry in the morning. And then we measured by using hydrochloric acid how much CO2 we collected at night, and that we had collected half of the CO2. So she did that science project, won a prize for it. All of things went nice and great. And then a few years later, I got interviewed, and somebody asked me, this must be a really horribly hard problem. And I said, oh no, this is actually not a hard problem. Even my daughter can do it because she did it for a science fair.
Klaus went ahead to publish a paper on Claire's discoveries, along with 2 of his colleagues at Los Alamos. The paper explored whether mitigating greenhouse gas buildup by extracting carbon dioxide from the air was worth further study. Several carbon removal options were also explored, like using certain minerals to enhance the natural mineralization of carbon dioxide. This is a task he had envisioned the Oxons taking on, but Klaus chose to focus on direct air capture. The paper concluded that despite the inherent disadvantage of not capturing carbon dioxide directly from more concentrated emission sources like a coal-fired plant emitting flue gas, there are also advantages to direct air capture. One of the advantages, according to the paper, was the flexibility in scaling to a large size to take advantage of economies of scale. The other was the great siting options to take advantage of existing infrastructure and lower transportation costs for sequestering the carbon dioxide below ground. The biggest challenge with this plan would likely be the amount of energy required. Some notable scientists completely disagreed with the paper's conclusion that the cost of pulling carbon dioxide from the air could eventually be less than 25 cents per gallon of gas. That can be likened to $25 per ton of carbon dioxide. David Keith was one of those scientists. While he had some reservations about Klaus's conclusions, David had a chance to work these out with Klaus as part of an analysis group at Carnegie Mellon University.
Most professors would start up companies, start them to commercialize some little innovation from their laboratory or their group. I think carbon sharing started in a really different way. It basically grew out of a public policy and techno-economic analysis group at Carnegie Mellon, where Klaus Lackner had come along, and he was absolutely the first person to think about, I think the first person to use the word direct air capture, I assume, the first person to really think about direct air capture as a thing that could be used for climate, where there's earlier non-climate applications. But I felt that he was over-optimistic about the cost of DAC. Mm-hmm. And so as part of a sort of broad effort in this group at Carnegie Mellon to do techno-economic analysis of a bunch of climate technologies that mattered, we started thinking about that. And then me and Greg Lowry and Klaus collaborated on a Department of Energy proposal. And then he came to meetings as we began to think about how we could do kind of a techno-economic analysis of DAC.
While David thought that Klaus was being over-optimistic about the cost of DAC, Klaus decided to move his theory from desktop to lab and eventually to demonstration.
We're kind of a unique lab where we have a conventional chemistry lab, and then lab benches for small benchtop experiments. Adjacent to it in the same space, we have our fabrication area where we'll put things together. My name's Jason Kamon, and I'm a mechanical engineer here at the Center for Negative Carbon Emissions.
Their center at Arizona State University is the result of Klaus's work on direct air capture technologies. One specific modular and scalable prototype Klaus and his colleagues are advancing is called mechanical trees. They look like large cylinders, so they're more like mechanical cacti than anything. The idea is that natural airflow from wind would bring air in contact with specialized materials known as sorbents. These sorbents remove CO2 without the need for fans or blowers. This passive capture, which uses less energy than other DAC pathways, is what makes this technology unique. Once the material has become saturated with CO2, the mechanical tree collapses into its trunk, where the collected CO2 is removed as concentrated gas for use or permanent storage.
Right now we're looking at kind of a full-sized mock-up of the discs that'll be inside of the carbon collect mechanical tree. These discs are maybe approximately maybe 1.5 meters in diameter, and they have these wedge-shaped pieces of sorbent that'll sit inside of them.
For the uninitiated, what do you mean by sorbent when you're talking about CO2?
The sorbent is the material that absorbs CO2 and removes it from the atmosphere. When the mechanical tree is raised, the gap that's between each disc is represented down here, about that 2-inch gap. And then when they're collapsed inside of that collection chamber at the bottom, the discs will sit on top of each other. What we're hoping to learn is that this technology can kind of be built at a industrial scale and be usable.
Great. When you say industrial scale, like what kind of scale are we talking about? Talking about 100 trees, 1,000 trees, 1,000,000 trees? What do you mean by scale?
At least thousands ultimately, because the idea is that these things can be produced and then distributed throughout the planet in clusters, maybe something similar to like a wind farm, but for collecting CO2.
So how long do you think it will be when I can buy one of these at Walmart or off Amazon?
Let's see. I don't know. What's a reasonable time? Like what, 5-10 years?
In the next episode of Scrubbing the Sky, we'll circle back to David Keith to learn more about the early days of carbon engineering and how he gained a big financial backer in Bill Gates, the billionaire philanthropist and founder of Microsoft.
Usually we don't have a deadline where you have to get the miracle by a certain date. Usually you just kind of stand by and some come along, some don't. This is a case where we actually have to drive at full speed and get a miracle in a pretty tight timeline.
Thanks for listening to Scrubbing the Sky. Please rate and review us on Apple Podcasts, Spotify, and your platform of choice. This podcast series is produced by Amit, Tandon, and Bespoke Podcasts, with help from Pat Kelly, Lauren Berkovich, and Chris Kelly at Kelly & Kelly. Additional support from Paul McKendrick, Eva Boynajescu, our interviewees, and our reviewers. And I'm Ed Whittingham. This series is made possible through the generous support of the Conscon Foundation, the Trache Foundation, the Grantham Foundation, Linden Truss and Spitfire, and the Auxilium Foundation. For more information about Paul McKendrick's book that this series is based on, please visit www.scrubbingthesky.com. Thanks for listening.